Imagine waking up in Southern California and discovering that the most dangerous part of the earthquake story is not the last major rupture people remember, but the silence that came after it. Not silence in the emotional sense, not silence in the headlines, geological silence, the kind that lets strain build year after year, decade after decade, until an entire fault system begins carrying more stored energy than at almost any time in living memory. That is the real reason scientists are watching California so closely. A new long-range earthquake model suggests that one of the most important fault junctions in the state has reached stress conditions higher than anything seen there in the last 1,000 years. And if that sounds dramatic, it should, because the place we are talking about is not just another line on a map. It is the point where two of Southern California's most dangerous fault systems approach each other in a way that could determine how the next major earthquake unfolds. Tonight, I want to walk you through exactly why this matters, what scientists found, what this does and does not mean, and why a long quiet period can actually be more unnerving than a swarm of smaller quakes. By the end of this video, you will understand why researchers are treating this part of California like a kind of geological gate, why that gate may be under more pressure than at any point in the last millennium, and why the phrase most people should remember is not overdue panic, but accumulated risk. Because this is not a prophecy video. This is not one of those videos that tells you a giant quake is definitely coming next Tuesday at 4:17 in the morning. Earthquake science simply does not work that way. But what science can do is tell us when a system is carrying unusual levels of strain, when historical patterns start to line up in troubling ways, and when the consequences of a future rupture could become much more severe than most people realize. The location at the center of this story is Cajon Pass, a corridor in San Bernardino County that most people know as a transportation route and almost nobody thinks of as an earthquake gate. But beneath that landscape sits one of the most consequential tectonic relationships in California. The southern San Andreas Fault and the San Jacinto Fault system are both major players in Southern California earthquake hazard. They accommodate a huge share of the motion between tectonic plates in this region, and near Cajon Pass, they come close enough that what happens on one can influence what happens on the other. That is what makes this junction different from a single, isolated fault segment. If one side ruptures, the real question is whether the rupture stops there, or whether it jumps, transfers, or continues in a way that involves both systems. That difference could mean the difference between a very damaging earthquake and a far more destructive one. Scientists studying this region built a physics-based model that reconstructed roughly 1,000 years of earthquake history across these linked fault systems. They fed the model evidence from geology, dating methods, and the known behavior of past ruptures, then used it to estimate how stress has accumulated and shifted over time. The result is the kind of finding that immediately gets the attention of anyone who studies seismic hazard for a living. The current stress state near Cajon Pass appears to be at or above the highest range seen anywhere in that 1,000-year simulation. In other words, this is not just a busy fault system, it is a heavily loaded one. And the concern is not simply that one segment is highly stressed. The concern is that multiple fault segments may now be stressed in ways that make them more compatible with a larger combined rupture than with a smaller, isolated one. That idea is where the earthquake gate concept becomes so important. Think of Cajon Pass like a narrow doorway between two rooms filled with pressure. Sometimes the door holds. A rupture tears along one fault and stops at the junction. Other times the door opens and the rupture crosses through, linking both systems into a larger event. Scientists say this gate does not stay permanently open or permanently shut. It responds to the evolving stress conditions on both sides. If the stress on the two faults builds in different ways and at different times, the rupture is more likely to stay confined. But if the stress on both systems climbs into a similar high range together, the conditions begin to resemble the kinds of setups that historically allowed earthquakes to run across the junction instead of dying out there. That is what makes the present moment so unsettling. The issue is not only how much stress has accumulated, it is how aligned that stress may now be. One of the strongest numbers in the new research comes from the San Jacinto side of the system, where modeled stress reached 3.6 megapascals on a key section, surpassing anything seen in the 1,000-year simulation. On the nearby San Andreas segment, the modeled stress reached 2.8 megapascals, also near or above prior peaks associated with major historical ruptures. Now, those numbers may sound abstract if you do not spend your life thinking about crustal mechanics, but to scientists, they are not abstract at all. They are part of the evidence that this fault junction is not simply active in the everyday California sense. It is critically loaded. It is sitting in a configuration that demands attention. And when researchers say that conditions similar to those that historically preceded joint ruptures are now approaching again, that is not casual language. That is the scientific version of saying the system is carrying more potential than anyone would like. To understand why that matters, it helps to look backward. Southern California has seen earthquakes that behaved very differently at this same junction. In the Great Fort Tejon earthquake of 1857, a massive rupture tore along the San Andreas but terminated at Cajon Pass rather than continuing onto the San Jacinto system. That was one kind of outcome. But there is also historical evidence from earlier major events suggesting that some ruptures may have crossed the junction and involved both systems together. That difference is everything. A rupture that remains confined to one system is dangerous enough. A rupture that propagates across both could be much longer, involve more total energy release, and spread severe shaking across a wider region. This is why scientists are not only asking how stressed the faults are, they are asking whether the system now resembles past moments when the gate was more likely to open instead of close. And if that sounds like a technical distinction with academic value but little real-world meaning, think about what lies in and around this corridor. Cajon Pass is not empty wilderness. It is threaded with highways, rail links, freight routes, pipelines, power infrastructure, water systems, and the connective tissue of one of the most densely populated and economically critical parts of the United States. The greater Los Angeles region, San Bernardino, Riverside, the Inland Empire, and the Coachella Valley all exist inside the shadow of what a large Southern California earthquake could do. So when scientists warn that a joint rupture would have much larger consequences than a single fault event, they are not talking in vague disaster movie language. They are talking about transportation paralysis, broken utility corridors, fires, prolonged disruption, damaged hospitals, economic shock, and millions of people suddenly confronting the reality that the ground under modern California can still rewrite everything in minutes. Here's the part that always catches viewers off guard. The most troubling finding in this story is not that scientists discovered some brand new fault nobody knew about. It is that the danger has been building in plain sight for a very long time. California's plate boundary is always moving. The tectonic system does not pause because a city has grown larger or because people have become used to earthquake headlines. Stress accumulates even during calm decades. In fact, long calm periods can be exactly what allows strain to build into something more consequential. That is why geological silence can be so deceptive. People naturally assume that no recent giant rupture means less danger. In many cases, it can mean the opposite. It can mean the system has had more time to store energy, more time to lock, and more time to drift toward a state where the next big release could involve more than one part of the network. This is where a lot of bad earthquake storytelling goes wrong. It tells people either that a major earthquake is definitely imminent, or that because nobody can predict the exact day, the whole subject is basically guesswork. Both ideas are wrong. Scientists cannot predict the exact timing of a major earthquake with precision, but that does not mean they know nothing. They can identify where stress is accumulating, they can reconstruct how past ruptures behaved, they can estimate which faults are loaded, which segments are more likely to be involved, and what kinds of rupture pathways would be especially dangerous. That is what makes this new modeling work important. It does not tell us when the next big earthquake will strike Southern California. It tells us that one of the most important gatekeeping locations in the system appears to be more stressed than at any time in the last 1,000 years. That is not a date. It is not a countdown. But it is absolutely a warning worth taking seriously. There is another number that deserves attention here. Long-term earthquake forecasts have estimated that the Los Angeles region faces about a 60% chance of experiencing at least one magnitude 6.7 or larger earthquake over a 30-year window beginning in 2014. That does not mean one specific fault will rupture, and it does not mean the event has to happen this year. What it means is that severe shaking in Southern California is not a remote possibility to be pushed into some distant future. It is a normal part of the regional hazard picture. And when you combine that background probability with new evidence that critical fault segments near Cajon Pass may be carrying historically extreme stress, the issue becomes harder to dismiss as theoretical. A region can have a high long-term hazard and still go through long periods without a major event. But that quiet does not erase the hazard. It often deepens it. But raw percentages are hard to feel. Consequences are not. So let us make this vivid. A major Southern California earthquake is not just a story about collapsing shelves and a few broken windows. A large rupture on the southern San Andreas has long been associated with scenarios involving violent shaking across multiple counties, thousands of damaged buildings, long-lasting utility failures, overwhelmed emergency response, and severe regional economic disruption. One well-known estimate for a hypothetical magnitude 7.8 southern San Andreas event projected around 1,800 deaths. That is the scale of consequence embedded in this conversation. Now imagine a rupture scenario in which stress conditions at a key junction increase the odds that more than one fault system could be involved. That is why a study like this instantly grabs the attention of earthquake scientists. It does not create the danger. It clarifies the shape of danger that may already exist. Now, I want to slow this down for a moment because this is exactly where fear can outrun understanding. A critically stressed system is not the same thing as a guaranteed immediate rupture. High stress does not mean the Earth is going to break tomorrow morning before sunrise. Faults do not fail the instant they reach some universal threshold like a machine hitting a red line. Natural systems are more complicated than that. Friction varies. Stress is not perfectly uniform. Some segments creep, others lock. Fluids matter. Geometry matters. The legacy of previous earthquakes matters. That is why scientists speak in terms of scenarios and probabilities instead of certainties. But the absence of certainty should not be mistaken for comfort. If anything, uncertainty is part of what makes this story so serious. You can know the system is in a dangerous configuration and still have no ability to say exactly when it will decide to move. That is why the earthquake gate idea is so powerful. It gives people a way to understand the problem without oversimplifying it. Imagine one rupture racing toward a junction. At that moment, the future is not settled. The junction can act like a barrier, absorbing the complexity and stopping the rupture from growing. Or it can act like a bridge, letting the rupture pass through into another fault system already primed with stress. The same place can behave differently at different times because the state of the system changes over decades and centuries. That means the critical question is not whether Cajon Pass is inherently safe or inherently dangerous. The critical question is what condition it is in now. And according to the latest modeling, that condition is among the most concerning seen in the last 1,000 years. For a region built around dense infrastructure and massive population exposure, that is not a detail. That is the headline. So what exactly are scientists watching from here? They are not waiting for one magic sensor to light up and solve the mystery. They are watching the full behavior of the fault system over time. They look at seismicity, of course, but also at deformation, stress transfer, and how the long history of past ruptures fits into modern modeling. They watch whether smaller events appear in especially sensitive places. They compare how stress on adjacent segments evolves. They ask whether one fault is becoming more out of step with the other, or whether both are marching upward together. Because if both systems remain highly stressed in a similar range, the historical analog becomes harder to ignore. That does not equal a prediction. It means the structure of the risk becomes more legible. And in hazard science, a clearer picture of the worst plausible pathways is often the most valuable thing you can have before a disaster happens. This is also where a lot of viewers need reassurance, but the correct reassurance is not what people usually want. The reassuring part of this story is not that the risk is small. The reassuring part is that modern science is far better at understanding these systems than it used to be. Researchers can run sophisticated earthquake cycle models across centuries of fault interaction. They can test how one major rupture changes stress on neighboring segments. They can identify junctions that matter more than others. They can compare current stress patterns to historical ones instead of looking only at the latest tremor in isolation. That does not eliminate danger, but it does mean society is not blind. The problem is not ignorance. The problem is whether people are willing to act on what is already known, because a warning that is ignored behaves almost exactly like no warning at all. And there is one warning that deserves to be said plainly. The next great Southern California earthquake does not need to happen directly under downtown Los Angeles to become a regional crisis. Fault geometry, shaking intensity, local geology, infrastructure exposure, and cascading failures can spread consequences far beyond the rupture itself. Transportation can fail in one place and create shortages somewhere else. Water systems can be damaged in a corridor and disrupt communities far from the initial break. Hospital capacity can be strained across county lines. Ports, warehouses, logistics hubs, and rail freight can turn a geological event into an economic event almost instantly. That is why this story cannot just dwell on magnitude numbers. The true danger is system-wide. The rupture is the trigger. The crisis is what unfolds through every network that modern California depends on, once the ground begins moving faster than the state is prepared to handle. This is exactly why the long quiet period since the last truly massive Southern California rupture is so unnerving to experts. The 1857 earthquake is ancient history in human political time, but in tectonic time, it was almost yesterday. Fault systems do not care about calendars. They care about loading rates and frictional resistance. More than a century and a half without a comparable regional rupture can sound like stability to the public, but to a seismologist, it can also sound like a system that has had a very long time to reload. Add to that the possibility that key segments on both the San Andreas and San Jacinto systems are now carrying historically high and relatively aligned stress, and the picture becomes harder to dismiss. Again, nobody serious is saying the next rupture is guaranteed to jump the gate. What they are saying is that the conditions associated with the more dangerous option appear to be building again. Let me say something else that may sound paradoxical, but is central to earthquake preparedness. The goal of a video like this is not to make people afraid of every creak in the wall or every truck that rattles a window. The goal is to help people fear the right thing at the right level. You should not live in permanent panic because California is tectonically active. But you also should not treat a region-wide earthquake risk like a background myth that belongs only in documentaries and historical photos. The correct emotional setting is disciplined respect. Respect for the fact that major earthquakes happen here. Respect for the fact that some fault junctions matter far more than others. Respect for the fact that scientists are identifying stress patterns that look unusually severe. And respect for the idea that preparation is not paranoia when the hazard is real and the timeline is unknowable. Now let us get back to the science, because the mechanism itself explains why this junction matters so much. The San Andreas and San Jacinto faults are not just separate cracks running side by side forever. They are part of a larger system of strain partitioning across Southern California. They share the burden of plate motion in different ways across different segments. A junction like Cajon Pass matters because it is where rupture behavior can become nonlinear. A quake does not simply follow an abstract line on a textbook diagram. It navigates friction, geometry, and the current stress landscape. If the stress fields on both systems are favorably aligned, rupture can do something that is far more dangerous than staying on one fault. It can cross. It can connect. It can turn a severe earthquake into a broader, multi-fault event. That is why researchers describe the junction not as scenery, but as a control point in the future of Southern California hazard. And here is the most unnerving part of all. The model suggests that this control point may not just be busy, it may be historically primed. In the 1,000-year reconstruction, some present-day values exceeded earlier peaks associated with major events. That kind of language should stop viewers in their tracks because it reframes the entire idea of modern California earthquake risk. We are not only talking about a region that is always dangerous in some generic sense. We may be talking about a particular moment in the stress evolution of the system when one of its most consequential junctions sits in a more loaded state than it has for centuries. Again, that is not a prophecy. But if you are responsible for highways, aqueducts, hospitals, pipelines, rail, emergency planning, or simply your own family's preparedness, you do not wait for prophecy. You respond to the clearest available picture of risk. That is where the public conversation often lags behind the science. People hear that prediction is impossible and translate that into inaction. But hazard assessment is not fortune-telling. It is about identifying what kind of event a region should be ready for, even when the clock is hidden. Think about how absurd it would be to ignore hurricane zones because nobody can name the exact landfall date of the next major storm years in advance. Earthquake readiness should work the same way. If the system is critically stressed, if the region is dense with vulnerable infrastructure, and if the consequences of a joint rupture would be dramatically worse than a confined event, then the practical response is obvious. Retrofit where possible. Harden infrastructure. Rehearse emergency plans. Secure the inside of homes. Prepare for days without normal services. Treat the quiet period as the time you still have, not as evidence that nothing will happen. And yes, I know some viewers will ask whether this means California is more at risk than ever before. The careful answer is that key segments near Cajon Pass may be more stressed than at any point in the modeled last 1,000 years, which is a very specific and very serious statement. But risk is more than one number. It includes exposure, building resilience, preparedness, emergency response, and how the actual rupture unfolds if and when it happens. California today is far more populated and interconnected than it was during earlier historical earthquakes. That means even if science is better, the stakes are also larger. Millions of people live within the sphere of consequences from a major Southern California rupture. Critical freight corridors pass through the same landscapes that geologists study for past breakage. The state is simultaneously better informed and more exposed. That combination is exactly why the next major earthquake remains one of the most consequential natural hazard scenarios in the country. There is also a psychological trap built into California earthquake culture. Smaller quakes can make people feel either hyper alert or falsely reassured. If a small quake happens, some assume the system is releasing pressure and maybe preventing something worse. If nothing happens for a long time, others assume the danger is fading. Real fault mechanics are not so simple. A small event on one segment does not necessarily relieve the dangerous stress state of a much larger system. In some cases, the more important story is not the little quake itself, but where it happened, how it changed neighboring stress, and what it reveals about a junction that may already be heavily loaded. That is why this video is not built around a single recent tremor. It is built around the bigger discovery that the gate itself may be sitting in one of the most concerning configurations scientists have ever modeled there. So what should an audience member actually do with all of this information? First, understand that the lesson is not panic, but timing. The best time to prepare for a major earthquake is before there is a specific short-term warning, because there may never be one. Second, take infrastructure seriously. If you live in Southern California, know where your water shutoff is. Secure heavy furniture. Keep lighting, medicine, backup batteries, food, and water ready for more than a single day. Third, think beyond the moment of shaking. The hardest part of a major earthquake is often what happens after the first 90 seconds. Roads fail, power fails, phone networks clog, families get separated, routine disappears. Preparedness is not about surviving only the first jolt. It is about surviving the broken normal that follows. And finally, stop waiting for a magical certainty threshold. The science is already clear enough to justify action. And here is the point most people miss, because the most important part of this story is also the easiest one to overlook. The danger is not simply that California has major faults. The danger is that some of the most consequential pieces of that system may now be stressed in ways that make a bigger, connected rupture more plausible than people assume. That is the real story. Not apocalypse, not prediction, configuration. If a critical junction is loaded, and if multiple linked segments are approaching the ranges associated with past large joint ruptures, then the future of the next major earthquake may depend less on one fault acting alone, and more on whether the gate holds. That one idea changes how you think about everything from emergency planning to infrastructure resilience to the way a single quiet decade should be interpreted. There is a reason scientists chose careful language when discussing these results. They are not trying to scare people. They are trying to describe a system honestly. The current stress state is concerning. The geometry of the region matters. The alignment of stress across the two fault systems matters. The consequences of a joint rupture would be substantially larger. And none of this provides an exact clock. That combination of seriousness and restraint is exactly how trustworthy hazard communication should sound. If anyone tells you they know the exact time of the next great California earthquake, ignore them. If anyone tells you that a 1,000-year stress extreme at a major fault junction is meaningless because no date comes attached to it, ignore them too. The truth lives in the uncomfortable middle. The system appears heavily stressed, the hazard is real, and the timing remains uncertain. So let me leave you with the clearest possible takeaway. California is not suddenly dangerous because of one new study. California has always carried major earthquake risk. What this research changes is the sharpness of the picture. It suggests that at Cajon Pass, where the southern San Andreas and San Jacinto systems interact, current stress may be as high as or higher than anything seen in the last 1,000 years. It suggests that the relationship between those faults may now resemble conditions that historically preceded more dangerous through-going ruptures. It suggests that the difference between a single fault disaster and a larger multi-fault event may depend on a gate the public rarely thinks about. And it reminds us that geological silence should never be confused with geological safety. If the next great Southern California earthquake begins tomorrow, next year, or years from now, this much is already true. The system is being watched because the stakes are enormous. The faults do not need headlines to keep loading. They do not need attention to keep accumulating strain. They will keep moving at tectonic speed until one day part of that stored energy is released. Our advantage is not prediction. Our advantage is preparation while the quiet still holds. And that may be the most important message of all. The silence in California is not empty. It is loaded. And scientists are watching because they know that when a fault system goes quiet for too long in a place like this, the next sound it makes can change everything.